computer and start webinar. Here we go. And get back to the first slide. Quick, get back to the first slide. Click, get back to the first slide. Okay. Welcome, students.
Hello, hello.
Hi, everybody. All right. What a special day we have. What a special guest we have today. I'm so excited about this. So let's get started. All right. I think we have, the numbers are 40 people, which is about right. We usually have 30 to 40, about 50. Wonderful. Welcome, everybody, to CS61C Week 14, Warehouse Scale Computers. Woo! Great to have you all here. Great to have you all here. Let's jump right in and talk about the agenda. Our amazing guest is Professor David Patterson. I believe this is our first Turing Award winner, Bora, on our as our guest panel. We've had the DARPA lead. We've had CTOs of big companies. It's been an amazing semester. But this is the first time we have a Turing Award winner, which is the highest. It's Nobel Prize in Computing, if you don't know. So we're going to jump into David in about 10 seconds. But the agenda for today is, after talking to Dave, we have a Computing in the News, as we always have. Then midterm score update. We have some midterm scores to release to you, and we have some news. So that's exciting. Then we'll do a schedule, and then ask us anything. So, boy, it gives both Bora and myself and everybody on the staff the greatest of pleasure to invite Dave Patterson, our colleague and friend who helped build this class. By the way, this isn't just a random Turing Award winner. This is a Turing Award winner who has contributed significantly to, Dave, I think you also won the Karlstrom Award. I think you've won like every award ACM has to give. It may be one of the most honored people in the entire department, arguably the whole campus. Dave retired recently, Professor Emeritus now, and he's now working as a distinguished engineer with Google. Some exciting things. Maybe he'll share some of the fun things he's working on with there. He's the vice chair of the RISC-V Foundation, and he's known for partially inventing RISC, RAID, 61C, the textbooks that are the most popular textbooks in the entire planet. By the way, in computer architecture, there's no textbook that's more popular than Dave and Hennessy's book in architecture. So what a gift of his time and by the way, Dave was the first person I taught with in 61C. He was the one who taught me what 61C was like. So I owe him everything I am in 61C, I owe to Dave. So Dave, thank you so much for the time and for joining us today. What a delight.
Oh, thanks. It's always great to try and catch Dan's enthusiasm, which is contagious. I thought I'd start out with talk about 5 minutes, tell you about RISC-V, and then we're just going to open it up for questions.
Sure.
Oh, I can see the slides. Cool.
Yeah. Oh, perfect. And by the way, you have more than that. We have a lot of time. We have, I think, I'm looking for about 30 minutes. So don't feel like you have to rush through this. Good. Yeah. Don't rush through it.
I'd be happy to do questions and answers, either from you guys or from the
Wonderful.
students. So the story goes back to 2010, and there's a research project right there in Soda Hall where it was time for us to do computer architecture research. In fact, Bora was involved with this at that time. And this was led by our colleague, Krista Asanovich. And he wanted to do computer architecture research. And as you know, the vocabulary of computers is the instruction set architecture. Well, the two obvious choices were the x86 and ARM, but it was impossible for two reasons. First, they were very complicated commercial instruction sets, thousands of instructions. And even if we wanted to, they protect those instruction sets because they own those instruction sets and they don't want to let anybody have it. Even us, even though Intel was one of our sponsors, they wouldn't let us do that. So we had to develop our own instruction set. So Krista Sanovich and two star grad students, Andrew Water and Yunsup Lee, decided, okay, we're just going to slap something together in 3 months. Well, it took them 4 years, although along the way, they built some hardware. So it's a instruction set that's informed by actually trying to build it. And it actually got better over time. It actually got simpler over time, surprisingly. And the original idea was, well, as researchers, we want to use it, and lots of other researchers will have our problems. So we'll make the instruction set, which, as you understand, is just a specification, right? The instruction set tells the hardware how it's supposed to work, but then the hardware itself is a separate thing that implements that instruction set, like Ethernet and Ethernet standard Ethernet controllers. But there wasn't a lot of uptake with other academic units. The surprise was 4 years later, industry started showing interest. They really liked the idea of an open instruction set. And once we started talking to them to understand why is industry interested in our kind of research instruction set, then we thought, well, that's a great idea to try and have an open instruction set. And as an analogy is just like an open source operating system. Linux is probably the most popular operating system today. Could we do something similar to like that for an instruction set architecture? So Krista and I wrote a technical report. The instruction set should be free, a case for RISC-V. And I've learned recently, because we just celebrated the 10th anniversary and talked to a lot of people at the time. Actually, a bunch of people read that paper, and that got people to decide, okay, we're going to use RISC-V because of the arguments in that paper. Okay, next slide. So let's go over RISC-V. You've been using this in the class, right, Dan?
Yep.
Okay, so what do I think is really important? First is free and open. Anyone can use it. I think that means since everybody or many people are using the same instruction set around the world, it's more competition, and so I think it'll be more innovative. Particularly for startup companies or small companies, for proprietary instruction sets, the first thing you have to do is sign a contract. They say, well, okay, I'll pay you this much money up front, and then we'll give you a fraction of every chip that we sell. So you want to negotiate that contract carefully to you want to be profitable. So that takes a long time, and besides money. So what's nice about RISC-V, if you're a small company or a startup company, you can just say, I'm going to use RISC-V, and I'll figure out who I'm going to get the processor with later, because anyone can use it. So that's a kind of a big business advantage, independent of its technical qualities. Secondly, I think of it as it's really elegant. Because of classes like 61C, exactly 61C, when you try and teach assembly language programming, you don't want to show people the whole instruction set, because it's, it can be hundreds or thousands of instructions. So there's no real pedagogic value to that. So what you do is you subset it. You say, here is the essence of that instruction set. RISC-V, because it came out of academia for teaching as well as research, that subset is official. So those 47 instructions in RV is the whole simplest instruction set. So all RISC-V software will execute in just those 47 instructions if you want. So that makes it true. It's a new idea for instruction set architecture. Usually what happens is they start small, and over time they get bigger and bigger and bigger, kind of as you'll see as you get into middle age, your bodies will probably get bigger. But the instruction set, RISC-V is going to stay skinny for its whole life. How does it accommodate other applications? It has optional modular instructions, like you've seen the floating point instructions or the atomic instructions or the compact instructions. Those are optional if it matches your situation, but you don't have to use them. So that's a new idea for instruction sets. In the past, every time you added a set of instructions, every implementation of that processor for the next several decades had to also implement it. For RISC-V, it's optional. So those are two, a simple core and modular options are two big important changes, because that can make it much more targeted for the application. The third big idea, which is kind of easy to do in 2010 when we were doing it, is we knew that it was going to be important to add accelerators to instruction sets. We knew Moore's law was slowing down. We knew that this change was happening in the technology, so you're going to need to add accelerators. So basically, we just left lots of opcode space in it. Now, that was easy to do now, but 20 years before that, people didn't think that was important, so they kind of filled up the opcode space. So it's hard to add more instructions. It's easy in RISC-V. Not surprisingly, in 2010, we thought the future was at the edge and in the cloud. So we wanted to work well in the cloud and at the edge. So it has both a 32-bit and a 64-bit address. Shockingly, because the biggest mistake you can make in computer architecture is run out of address bits, that's not going to happen in RISC-V, because we also have a 128-bit address space version. We're not probably going to need that for a few years, but it's nice because if instruction sets are successful, they can last for 30, 40, 50 years. We've already, when it's time to go to 128-bit addresses, we'll be there. And finally, because it came out of academic roots, and once the graduate students graduate who worked on it and faculty get distracted, then it can kind of fall apart because the faculty aren't paying attention anymore to that project. Like Linux, we started a foundation, it's called RISC-V International, and it owns that instruction set and is evolving that instruction set. So that's why it can last for decades, even though academics can't, keep that much attention. And then finally, in this kind of new world, people are worried what's in their computer hardware. They're worried that there's some trap door in there doing something nefarious they don't know about. So by being an open instruction set, several countries all over the world have had those concerns. They're worried about getting technology from a competing country that might have, be an adversary. So you can design your own cores. And also because the open architecture allows open source implementations like written in Verilog or System Verilog or something like that. You can expect it. You can know what's inside your computer so there aren't any secrets. So these 7 bullets are what distinguish RISC-V and why there's a lot of enthusiasm for it. Okay, next slide. This is RISC-V International. It has more than 600 members in 50 countries. It's a really worldwide phenomenon. Depending who you talk to, they think, oh, this is our continent. You talk to the Europeans, they say, oh no, RISC-V is primarily European, or in North America, well, it's primarily North America. Or in Asia, oh no, we're the center, right? So they argue about it. And there's 2,000 people participating in the various projects to expand the architecture in different modular ways. So to try and convey this enthusiasm, the next slide, we'll see if that is a video. It's the 10th anniversary. We were going to have a party, but quarantine canceled that. So we put a video together instead. If you go to this website, there's a variety of videos that we've done kind of to document history. This is the 3-minute version that tries to capture the enthusiasm. So if you guys could play that, that'd be great.
Yep. All right. Bora's gonna take over and do that here.
See if it comes through.
All right.
RISC-V needs a theme song.
Beautiful.
Like we built this city, or something that has.
You make it louder?
Because that's what I feel. I see passion and dedication and an emotional attachment to.
That's as loud as it goes.
Okay.
That is so energizing that for those who haven't joined the community yet, come on in. It's a really, really powerful place to be.
I'm actually quite impressed. I think the kind of energy that is going into it, and the way you have got so many parties together is absolutely wonderful.
At the very lowest level, they have a common lingua franca. If there is a lingua franca, then we can start building standard computers. Computers are getting them.
Oops, the sound.
I clicked the mute by accident. I'm sorry.
Oh,
It's on me.
The option that is available.
Sorry, my bad.
Is to become all pervasive. You can't build a society on proprietary foundations.
The key differentiator for RISC-V from other processors is the openness, the fact that you don't need to sign any agreement whatsoever to just start using it. With this, you can just download it. You don't have to ask anyone's permission, and that is a fantastic difference.
Now that I'm doing architecture, I use RISC-V, and I get so many things for free. I can focus on adding value on a few instructions and leverage tens of millions, hundreds of millions of dollars invested over the last 10 years. You go that much further by being able to leverage that infrastructure.
We had a workshop where we announced that we are going to put RISC-V in every GPU and every chip that we have.
Starting this year, 95% of resources are put in RISC-V development.
When Western Digital announced that we were going to transition 1 billion cores, I essentially tried to replicate that momentum that IBM's $1 billion investment did to Linux with RISC-V.
Today, RISC-V is a movement that can no longer be stopped. The conversation started to change to why not use RISC-V as opposed to the early years where it was like, why the hell would I use something other than what I've always been using?
RISC-V is the Linux of the processor architecture world. It's the transformation to an open source platform that allows many, many more innovators and inventors to contribute to the advance of the technology.
I think of ARM as a company that has paved the way for RISC-V. It is always destined to act as a place filler in the history of computing as a precursor to RISC-V.
There is an immense opportunity for RISC-V to be in 5 years the leading ISA for computing. I mean, it seems to be incredible, but it doesn't look so impossible now.
Okay.
All right. Dan, do you want to take over the slide?
Yep. I got here.
I got one
right
last
now.
slide, and then we do.
Yep. Perfect. Here we go. Oops. Yoink. There.
Yeah. So this idea that came up in the video that some of the people involved, I really like the idea of a lingua franca. Basically, we showed you RISC-V in this course, and basically all the instruction sets are about the same. It's not like one is gigantically better than the other. So as was pointed out when we talked to the pioneers of RISC-V, if we just got one of them right, we could just all embrace that and we'd have a real lingua franca for instruction sets. And as Madhu from India pointed out, if it's going to have a lingua franca, it needs to be open. So we think that's our goal, right? And by the time you guys, if you're freshmen, by the time you graduate, we'll see how close we are, or maybe if you go to graduate school, by the time you graduate, by then it could be the most popular instruction set. It's certainly capable of going from the smallest to the largest things. There's no technical thing involved, challenge, but there's lots of business issues that have been happening. But this would be very exciting if instruction set that came out of Berkeley, in part to help teach 61C, became the instruction set that everybody in the world used. Okay, with that, I'm ready for questions.
And we have a couple queued up already. Bor, you want to grab them?
Dave, I mean, half of our labs are now RISC-V, and projects in 61C are RISC-V, but take a look in about a year and a half. I think all four will be. When we have more RISC-V hardware available and affordable, I think we can switch the whole course.
And when the Hive, I mean, when the Hive is all RISC-V, I can't wait till that day. That would be wonderful.
Well, there's a project that I'm heading up that's called the RIOS Lab. It stands for RISC-V International Open Source Lab. So there's a joint effort between Tsinghua University and Berkeley that's located in Shenzhen that's been around for, this research institute's been there for 6 or 7 years. And we're starting a new project there called the RIOS Lab. And the first thing we're going to do is build what we call Pico Rio. So this RIOS is Spanish for rivers. And so we think of the RIOS Lab as collecting resources from all over and creating this powerful force like a river. And Pico Rio, or Little River, or Tiny River, is going to be a Raspberry Pi-like board that's based on RISC-V. So it'll be trying to be open source as possible, but instead of using the ARM processor, it'll do RISC-V. And our goal is to make that a lot less than $100. So we're going to do that for the first half of 2021, we hope. And so we hope to supply something that students could use that runs RISC-V and do software development. So, okay.
All right, we got a few questions from the students. Ready? So the first one, this is an interesting one. This was the same question was asked when Andrew Waterman and Yusuf were guests over here.
That's right.
Andrew was
advisors answer to this one. What aspects of the currently frozen RISC-V ISA, if any, do you disagree with or would change if you could?
Me? Yeah. So I mean, Krista Asanovic is just, a real, he's kind of a mile wide and a mile deep. He knows a lot of things and he knows them really in depth. And he really likes to micro-optimize. So that explains the funny swirled address bits. It actually does say some hardware.
That was the same answer.
Right. There's a bit, and then there's a bit, and then
it saves some hardware in the very lowest end designs. But for me, in terms of the cost is having to explain it, I think I would have just done straight address bits, and which would have hurt the low end designs a little bit, but it would have been a lot easier to explain. I think that is the one that stands out to me.
Yeah, I think both Andrew and you are blaming it on Kirsty.
No, I think
that's brilliant.
I think Andrew. I mean, it's kind of like I've known Krista since he was he took classes. I'm old enough that he was a grad student here.
I was also Dave's grad student.
Yeah, But he just really, he kind of enjoys puzzle solving. So for him to kind of play with the address, play with the opcode bits, and I can align these 4 instructions with those 4 instructions, and that might save a couple of gates here and there. So it's like puzzle solving, like people enjoy to. He likes doing stuff like that. So for him, it was kind of fun to play with, muck with the opcodes to get that little optimization. So it was part of his personality. So yeah, Krista did that. Nobody else would have taken the time to do that I know.
I like doing that too. I have to admit it.
Okay, well, Bora. So it's like Carnot maps or something like that.
Right.
Yeah, we haven't covered Carnot maps in this class. We'll leave it for later. Okay. Here is another question. This one is kind of, we answered that, but maybe Dave can say, why do computer manufacturers not adopt RISC-V now, given its advantages over other ISAs such as x86?
Yeah, so, there's first of all, hardware is not like software where, you do a startup company and 3 months later you got a product, right? You have to design it, then you have to manufacture it, and it takes a couple of years. I've been I've known industry some, but I've been at Google for 4 years. So 2 or 3 years to start a project before a product comes out and actually deploy it. When it's a real product, it's got to work. That's typical. So partly it's happening and we can't see it. The other thing is that you guys don't know this, but Intel had this problem. How do people know whether there's x86s and things? So they did an advertising campaign on television called Intel Inside, just to let you know,
right?
Here's this thing. It's called an IBM PC, but actually it's got an Intel part in there, and they did advertising for that. So we're not going to be able to do that with RISC-V. So there's going to be a lot of stuff that you use that has RISC-V inside. So for example, NVIDIA GPUs have RISC-V inside. Western digital disk drives, RISC-V inside. Samsung cell phones, RISC-V inside. So there's a whole bunch of them that we know have RISC-V in them, but it's going to be hard for people to notice it. We talked to
and there's no budget, right? There's not. I mean, maybe the foundation might decide to do a similar kind of RISC-V inside thing, but I mean, it doesn't have the pockets.
Ask for funds from companies.
Right.
And spend it in advertising.
No, not happening. Yeah, not happening. Yeah, don't wait for it. Exactly.
So it takes a couple of years to get out there, and that's why I wanted to show you that video. What Stefan said. It's gone from, well, why should I take any risks with this instruction set to like, wait a minute, this is working.
Right.
Why shouldn't I use it? So that's going on. The places where it'll be the most difficult is ones, now that you guys understand this, that require binary compatibility either with ARM or x86. So where does that matter? PCs, the IBM PC, binary compatibility. Now, on the other hand, Apple abandoned the x86 instruction set like a month ago.
Right. Yeah.
Changed instruction sets. So that's hard for most companies to do. The other one would be the smartphones, where you distributing applications in binary in the ARM instruction set. So those two will be tough. But going forward, if you're going to do something new and exciting that's better than a cell phone, then you can pick whatever instruction set you want, because kind of binary compatibility is not as important today as it was in the past. And so that lets us innovate in instruction set architecture. And then here comes this new open one that is that has all kinds of potential benefits. And so I think we're going to see, like I said, in the next 5 to 10 years, I think it's going to get very popular, and you'll be able to check that.
All right, here's another one somewhat related to that. How does RISC-V plan to supplant extremely legacy systems like banking and medical computers?
Well, that's a really hard one. Like the IBM System 360, which dates back to 1964. IBM bet the company on this idea that you could have binary compatibility across the whole family of machines, and they won that bet. Those so-called mainframes, this was 7 years before the first microprocessor. That instruction set is still alive and well. It's still doing $10 billion a year of business.
Wow.
So, it kind of, it's interesting. Can you capture the existing applications? But it's more exciting from my perspective to get the new applications, the things that haven't been built yet. If those are going to be in RISC-V, and if, those older instruction sets have legacy code that can last for a long time, That's fine. The other possibility that people talk about is what's called binary translation, where you actually treat the instruction set as if it's a programming language and compile it into another instruction set. That's a topic that people have worked on over the years. You know, that might work. But for me, it's like, you know, if we're going to do 20 billion Internet of Things devices or 100 billion Internet of Things devices, it'd be more exciting to see these new apps using RISC-V than it is to, you know, kill the IBM mainframe market. That's less exciting for me.
Right.
All right, here's another question. This is a good one. We haven't thought of that one yet. For the modular extension instruction sets, is there modular hardware to match? I'm wondering how that general connection works.
Well, I think that's, you know, one of the exciting things about this transition, the open instruction set architecture, allowing open source instruction sets, and then this slowing down of Moore's law, meaning that we need to start building accelerators to improve performance and performance per watt, is, I would say, the hardware equivalent of modularity will be these so-called IP blocks. So what I've been doing at Google is building accelerators. I've been helping build accelerators for machine learning. So what we need is like a standard processor that runs like user interfaces and you know, compilers and operating systems, stuff like that, talk over networking, and these accelerators that make machine learning really shine. And that's the accelerators I've been building. So I would say that's the modular hardware equivalent of it. It'll probably be blocks written in System Verilog or something like that, that you can buy from somebody else and integrate on your chip, would be the modularity there. There's another idea that's catching on right now with the endings of Moore's law. Is Moore's law basically when he made his prediction? By the way, I'm sure you said Gordon Moore is an alumnus of Berkeley, right? You said that? Okay.
Yeah. That's your slide.
is that he was betting that every year, or in later revised every 2 years, twice as many transistors per chip, that basically was going to happen, more transistors per area, and the chips would get bigger. And they just got bigger and bigger and bigger over the decades. A new idea, now that Moore's law is starting right now, is what's called multi-chip modules. Instead of having one big chip, it's lots of little chips that are assembled on some kind of substrate. So another version of a modular hardware idea would be this multi-chip version, where you might have, instead of IP blocks you integrate on one chip, like, you know, typically what we've done in the past, maybe you'll have actually little chips that you're integrating together in some substrate that's really modular. So you could have a floating point piece, a chip, and you put it in the multi-chip things, or you leave out the floating point chip. So that's a possibility of what could happen. But basically, it's a very exciting time in computer design, because all the way things have been designed for decades doesn't work anymore. And so people are trying a lot of innovative ideas, and in instruction sets, the way we build hardware, all kinds of stuff.
By the way, this latest idea that they've shared about trying to build modular stuff out of chiplets is, you know, based on RISC-V, is Andreas Olofsson's idea. He just said he has a new startup. He was in that video.
He must have got it from me.
All right, here's another question. This is a good one. Are there vector instructions for RISC-V? Or are there plans to implement vector instructions like AVX in Intel? Just for a background, our current project is using vector instructions and intrinsics to do the parallelism.
Yeah. So one of the jokes is about RISC-V is that kind of what caught on is SIMD architectures, and there's a bunch of us at Berkeley who think those are really stupid designs. In fact, Andrew Waterman and I wrote a paper called SIMD Instructions Considered Harmful. But the contrast is these vector architectures, which are very elegant. So kind of one of the jokes is, it's called RISC-V. We called it RISC-V. It's called V because we wanted to have a vector instruction set. So Krista Sanovich and Andrew Waterman have been working very hard with a bunch of people at the RISC-V Foundation to finalize a vector instruction set. So it's, you know, it's almost done. People are starting to use it to build it. So yeah, there's one of the modular extensions is a real vector instruction set, which many of us are excited about and looking forward to.
How wide are they proposing?
It's up to you.
Oh.
You can, it's built in. That's the elegance of vector architectures, is you get to adjust that. But I think the people are talking about some of the first implementations are 256 bits per clock cycle or 512 bits per clock cycle. I think people are in that range right now. But that has long legs. It could be whatever people want to build.
That's exciting.
Yeah, it's fun. It'll be another year or two until we get hardware, and then Hive will be replaced. And here's another good one. I mean, this lots of inspiration from projects here. How similar is the way people design CPUs to our Logisim project? And Dave, remember Logisim? It got better.
Yeah, I remember. How similar? Well, people do design it in a hardware description language. They absolutely write it out. That's Logisim is a hardware description language, right?
Yeah, I mean, it is a graphical interpretation.
It's graphical.
Maybe I can answer this one.
Why don't you answer it?
Actually, this year we built a new backend for Logisim. Logisim now exports Verilog, which is a standard language that people use for building CPUs. And you guys don't know, but when did these project competitions, we actually went and synthesized your CPUs. We didn't tell you that we did that, but you actually, there does exist a live, since you submitted a Logisim file, but in the backend, we actually had the hardware description, the real hardware description of your CPU. And so we were able to compare them. This is
the embarrassing thing is Verilog's a kind of a terrible hardware description language, but it is popular. It's inelegant. So that's there's a lot of reasons not to write in Verilog. There's a variety of, even in industry, higher levels to generate. Verilog's kind of like almost writing assembly language way of designing it. And so a lot of tools use it. But if you wanted to get an idea of the low, kind of the worst case scenario of what hardware design descriptions look like, you'd look at the output of the Logisim to see it. But I think if you've done Logisim and then you could, if you take a follow-on course, I'm sure you could pick up the various hardware description languages and understand it.
Yeah, these questions keep flowing. At some point,
great. No, we're doing fine. We're fine.
Okay, and they're good. I mean, they're demonstrating.
Perfectly.
Yeah, right. That's right.
We're not at Stanford.
Crickets on their chat.
Yeah, they keep going. Here's I'll leave the last one, a second part of this one for the end. First, from Riata, wild technical question: would you or the RISC-V Foundation consider making instructions for quantum computing as it is getting developed?
So because I give this talk about things are slowing down and we need innovation, I get asked a lot about quantum computing. So quantum computing is a futuristic thing. There's a couple of national reports that talk about that maybe it'll have applications that'll work in 2030. And keep in mind that quantum computing is big computing. It's big science, right? Near 0 degrees Kelvin, trucks going by make it not work. So it will be like in a data center if it does work. So it's a really interesting topic. When I started graduate school, there were a bunch of people interested in nuclear fusion. They thought, I'm going to spend my career in nuclear fusion. Nuclear fusion still doesn't work. If it ever works, it's going to be really fantastic. We know it works. We look up the sun. Yep, that's nuclear fusion. But we haven't figured out how to put less energy in, get more energy out than we put in for nuclear fusion. So quantum computing is very exciting. I don't think it's going to be practical this decade. So it's a 2030 thing. But, if you're excited about it, that's really great. So, but I don't think it kind of doesn't make sense to have a quantum computing instruction. That's not the way quantum computing works. But there are people here you could talk to if you're excited about quantum computing. I'm sure there's many projects they could learn more about it.
Yep. Here is another one, and a few related ones. I mean, this is, there is a train of, you mentioned this. So here are the questions related to that. Apple's new M1 chip is ARM-based. Do you see the possibility of something analogous based to RISC-V, and how? Why?
See something, say it again.
analogous based on RISC-V?
Yeah. No, I would say this happens some in the RISC-V community where somebody had a processor design that was, I said, kind of these RISC architectures are all pretty similar. They had an existing design and they learned about RISC-V and they liked the idea of this openness and this community around it. And so they just changed the first stage of the pipeline. The instruction, after you fetch the instruction, you decode it. The second stage of the pipeline, that decoding, they changed the decoder and they could execute RISC-V. So if they can, that M1 design that's based on the ARM instruction set, they could pretty easily switch it over to RISC-V. So I think whenever ARM is successful in building something that's faster and lower power, to me, that's a great sign because I'm sure you could also do it in RISC-V. There's not, like I said, the instruction sets are all more or less the same. x86 is very different, but the RISC architectures, loads and stores, 32 registers, similar encodings, so they're kind of all the same. And that's partly, I think, for Hennessy and I, we got our Turing Award in part for our contributions to RISC and in part for that textbook. So we're kind of surprised that 35 years later, the best ideas are still RISC. 35 years of Moore's Law, who knows what would have happened, right? We're kind of surprised. But since that seems to be our best ideas there, any time something good's happens ARM, we think that's good for RISC-V. And assuming that a significant number of people will like the open model as opposed to the proprietary model.
And so here is another, this is another good question. And, there is another person who I'm thinking of who could be, who could answer this, one of your former students. Can binary translation be done in hardware?
Yeah, so as I think you know from the class, Intel, to its credit, once the RISC ideas went out, didn't give up. They put a 500-person engineering team together to build the Pentium Pro, as it's called. It came out in, I think, 97. And what they did, amazing enough, is translate from x86 into RISC instructions on the fly in hardware. So kind of a hardware compiler. Now, at that time, Intel's processor technology was a couple of years ahead of everybody else. So they had extra stuff on the chip, but their technology was years ahead. So they could hide that cost. So there's an example of somebody doing hardware translation on the fly. Now, there may be some, in one of these discussions I talked about it, somebody claimed there were some legal issues about translating binary instructions and executing them. And so like patents, whether you'd be violating some patent if you did that, I don't actually understand that, but I have heard that claim. So before you start your company, you should talk to some lawyer and see if there's some truth to that rumor that there may be, you may be violating some kind of patent if you were to do a hardware translation.
Yep, I actually know of a patent, I think, that that claims that. Yeah, we are getting two questions here. One, I'm going to rephrase some of these because we have still quite a few and we are running low on time. And I'm going to save Riota's second part of our question for the last. The one, so what are the plans for your books? I mean, I actually, my age, well, I'll reveal my age when I tell that I actually own first edition of the book. That's how I learned.
Oh, you're really old, Bor. You're really old, Bor. If you bought a book, wow, that's.
Yeah, I actually own the first, the second edition, and then like I skipped the third, maybe.
Yeah, it wasn't very good. Okay. Good. What's your question?
So how many total copies? Do you keep track of how many total copies?
We asked once, and I think the undergraduate's more popular. I think the graduate book was, I think it was 250,000 to 500,000, something like that. And the undergraduate one they certainly sell more. There's more undergraduates than there are grad students. This is over 30 years, right? So it's a number like that.
So
yeah, hundreds of thousands. Yeah.
Wow. And are there plans for a new edition?
Oh, absolutely. The undergraduate book, I just turned in the galleys for the second edition for the RISC-V version. I talked to Krista Sanovich about it, asked him based on teaching 61C, what did he recommend? He recommended going back to 32-bit addressing because, you know, it's when you're first learning instruction set, there's that confusion about 64 and 32, and there's a few instructions there. So we did that. I also don't tell them about the swirled address bits until chapter 4. I don't explain that. And chapter 4, we explain what multiplexers are, and I have a little table there that shows exactly how many 3-to-1 mux became 2-to-1 muxes because of the swirled address bits. And there may be a sarcastic tone to that section, but we emphasize more about fundamentally the bits can mean anything. You know, that it's kind of a strange concept that data can be anything. So I try and do more, kind of hit that one harder because people are surprised about that. So these are a lot of suggestions from Krista, second edition. So I just turned in the galleys, so it'll be for sale maybe in March or the next edition.
All right.
Next fall, definitely, yeah.
And here is one final question. What are a few words of advice you will give to folks who are just beginning a college CS career? And maybe we can expand that or narrow it down a bit to people who are just wrapping X61C.
Yes. So I, as Dan and Bora knows, I love giving advice. So you're gonna have to cut me off probably. I would say, you know, I'm sorry that you're going to college in this quarantine time. I've been around a long time. This has been the strangest year in my lifetime. So you guys survived that. I think you picked a great major. If you're in this to do computer science at ECS, you know, this is going to be a really exciting century, just like the last century was really exciting. There was no undergraduate degree in computer science when I went to school. They happened a couple of years later, and I kind of did it myself. I stumbled on this, but boy, when I did it, my relatives said, "Well, okay, good luck in computing." And then over the decades, wow, that was a really smart decision you made. I did it because I loved it, not because I thought it had a tremendous future, but it worked out really well. And I don't see anything slowing down in this decade. You know, machines starting to get more intelligence, more applications. It just seems like this is going to be a very exciting field. The part of Google I work on is called Google Brain, and that's one of the big proponents of the machine learning, the deep neural networking. I would definitely take statistics courses while you're there. That's, you know, it's computer science and statistics is the foundation of this machine learning. It's hard for us to know how big a revolution this is, how far it's going to go. It's already gone pretty far. It could change how we program. Instead of writing millions of lines of code, already there's some examples where we infer those lines of code basically from algorithms that look at the data. So I think it's going to be a pretty powerful force. You should think about going to grad school, right? Life expectancies are going up. I retired, and one of the best things about retiring was going to a retirement party. And she said the #1 correlation with longevity is education. And so people in this crowd are going to live a long time. And I had been thinking, looking backwards, that, boy, I'd be lucky if I get into my 80s. And talking to her here, I added a decade to my expectations. I expect to get to my 90s, mid-90s. You guys a lot of you will live to 100, get to 100 with advances in medicine and taking care of yourself. So that's a long time. So thinking when you're 21, boy, that's it. I can't afford to go to school anymore. You're gonna have really long careers. I would seriously consider graduate school. The last degree you can buy, no one's got. PhD is it. There's not like PhD plus, right? And spending 5 or 6 years getting acquainted to all kinds of the technologies that are going on, people still willing to teach that to you, and it's a ripe environment to learn, and you get trained how to do research on your own, give talks on your own. Part of the reason I ended up at Google is I wanted to do a sabbatical there because I didn't understand why they're hiring all the PhDs. And more or less they said, look at the training you get with a PhD. You can tackle problems by yourself. You know how to solve them. You learn how to communicate. Those are valuable skills. So they hire a lot of PhDs, even though they don't have big research projects. I think going forward, given life expectancies, PhDs, there's going to be more opportunities for people with PhDs. So you should seriously think about grad school, at least a master's degree. You'll have plenty of time to make money after grad school. Don't worry about that.
All right.
Great advice. Wonderful.
All right. Thank you, Dave.
Okay.
Thank you so much, Dave. It's great to see
Patterson.
you. This is Dave Patterson, everybody.
Hey, I can see you're still doing computing in the news. I think I started that.
You did start that. Thank you for that.
All right.
Wonderful.
All
All right.
right.
Take care, Dave. Beautiful. All right. Let me share my screen and get it here. That was what a delight, Bora. What a delight. My goodness. All right. So I think it's this window. See if that's going to work. Oh, okay. Let me try it again. Okay, here we go. Yoink. We got some news. Got to share the midterm scores. So excited about that one. So first we'll start with the computer in the news. Yeah, exactly.
This is a good one.
Yeah, 75. So here we go. Tesla Model X gets hacked through a new relay attack. Tesla said is pushing a patch through software updates. By the way, this is one of the benefits of having a software, an over-the-air software update. Normally, there's a software failure, you have to queue up a time. Well, I'm Subaru, I'm BMW, got to queue up a time to get back to the dealership. This is wonderful. You can update this there. But I also understand. I was reading the article that talks about there's a two-step hack. One of this is there's a key fob. Did you read that? You got a chance to read this? I was reading this while you were talking to Dave. There's a key fob that's used in the Tesla, and they were able to basically spoof the key fob to open the door. And then the catch is you can't just drive away. You can certainly, with the key fob, I think, roll the windows down, open the trunk, and open the door, but you can't drive away. And they say, however, once they're inside the vehicle, there's like a little port. Many cars have a little port where you can control, plug a laptop in with a serial port and talk to it. Within like a couple of minutes, he plugs into the port and he overrides it. He says, "Yep, okay, you can start driving." Drives away, and there's a whole video on this link. So certainly, Tesla cares about security in a great deal, and they're going to be trying to push out a fix very, very soon to fix it.
This does show a few really important things that again somehow we got this back into RISC-V court, right? The openness and understanding where building in security in the very root of our systems is going to be really, really important going forward, because there is a great comment over here. I liked it when the most advanced thing in my car was the radio.
The cars board I used to own.
Oh, I didn't even have a radio. Car. But the point here is, this is the big thing here is we like the convenience, and we will love to talk to our cars. In a few years, we'll be talking a lot more to our cars than we are presently. And there will be a computer, and that computer will need, or that set of computers will need to be very secure. There is a big debate over here how open this thing has to be, and RISC-V is making a really big push.
Right.
That things should be completely open down to the last single bit, and then it's a lot harder to if there is an attack, then it's very easy to trace it down and understand where it came from.
I mean, the topic about here is cars, obviously, and we're just trusting that Tesla does the right thing, right? We're putting our lives on the line to make sure Tesla does the right thing in terms of security, and so the car doesn't get stolen or hacked, or somebody puts the brake on or accelerates it during a traffic jam. On the other side, we're talking about voting machines, right? We just had a big election a couple of weeks ago, and so many voting machines are still closed systems. I think the future of voting machines, and David Wagner, our own colleague, is working on that, is thinking about, could you have a requirement from the federal point of view that says all voting machines need to be open in software, open in hardware, so that anybody can look. Obviously, paper trail, we talked about that's always critical. You boom, 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 you get paper trail, and then you hand the paper in as you vote. And maybe the voting machine is just your user interface to make voting easier for somebody. But I love the idea of mandating from the federal point of view an open hardware and software system to all voting machines. I think that'd be it would certainly put a wrinkle in many companies who already have investments there, but I think that's the right way to go moving forward.
It's an opportunity for the next set of companies.
Amen. Exactly. All right. So I wanted to share a midterm score update. Bor and I have written a midterm. And the midterm we wrote, we wanted to do better. We were really hoping for a better number than this histogram, but this is what we got. As you see, it's a very bell-shaped curve. Unfortunately, we've got a median of about 50%. I mean about 50%. And this is Bora and my midterm. This is what we tried. We tried to write this. And wait, Bora, did you play the slides here? Something looks wrong with the slide here.
Yeah, this the age maybe.
Yeah, this is weird because the year. This is fall of 2018. The last time Bora and I gave a midterm. Oh, this was the midterm. Okay, are you ready for this? This is what you get, ladies and gentlemen. The new school Bora. Dan, Cece, Justin, Jerry, Steven, everybody. Woo! 83%. Clobber, baby. Clobber all the way to the bank. I love it. Was that good? Did you like it? That was
they're traumatized.
Is that okay? Did you guys crush it or did you crush it? Oh my goodness. Okay,
and
now
this was not a lot
this
easier.
Was fair. This was a fair,
a lot easier midterm than what we had
no,
before.
This was a very fair midterm. I think that it wasn't like we just gave it to you. You guys did a great job. You helped each other. You guys are amazing. I want to tell you all, please do share this with your, link to this part of the video when you share this with your friends. Make sure you don't just read the answer. We're going to post this in just posted now. We just post the grades now, and we're not doing the silly joke about the old school, the new school. We'll just post the normal grades. It's posting right now. It releases right now. You guys crushed it. Crushed it. We are so proud of you all. Great job, everybody, studying so hard, working together through the COVID. Through the pandemic, you guys crushed 61C. You think you're awesome. Great job to everybody. Really, really wonderful job.
This is really a testimony that we streamlined a few things, and they are going to stay forever with this class. And this just shows that I think that the material went through.
And we were seeing this on the project scores bar. This is not inconsistent, right? The consistency that we're saying is you guys are doing an amazing job this semester, despite everything, right? Despite all the COVID and all the this and all the everything we're doing, we're trying to make this a better class. And I think clearly from your midterm, you guys are doing amazing. It's supposed to release now. I'm seeing some people saying they didn't get it. I'm really proud of everybody here. Proud of our team. I'm proud of our staff. I'm proud of everybody involved on the staff part of you and proud of the students. Now, that said, some students are still struggling, right? We can't always celebrate unless you all got a 45. We're not done yet. Okay, we still have work to do. Please come talk to our staff if you didn't do so well. People are on the lower end. Oh, by the way, this is very important. We didn't tell you this. This number includes all the people that had to do a retake for whatever parts they have. We had to put them the way the grades were. The software didn't know that they did have to do a retake. So they have zeros. So a lot of people have zeros or low scores. They're going to be totally replaced with the retake score. And that is still in process. And we're hopefully getting done in the next couple of days. So you guys, even if you got a low number, don't freak, because it'll say, by the way, I think we were able to put in the grade scope, it'll say to be replaced by the midterm retake. So don't panic if you got a zero because you knew it, because the retake isn't done yet. This is before the retake. So these numbers are going to go up. So 83 is the lower bound. We're going to be crushing this histogram once we get the retake scores embedded into here. So this is the beginning. This is the beginning of our conversation before the retake comes in. It's going to be amazing. So great job, everybody, in terms of this. Really, really well done. Let's do a quickie schedule. I know we're running late. We're at week 14. There's no lecture on Wednesday. Happy Thanksgiving, everybody. There's no lecture on Friday. Spend some time with your family if you can. If not, if it's on Zoom or if it's remote, please do spend time and be thankful for all the things we have in our society.
We don't have office hours this week.
Correct. No office hours this week. All the Wednesday, we basically shut down after Tuesday. We shut down after Tuesday and we revisit. And we try to make it so that you can really take the time to, enjoy your time. That's why we moved P4 to 12/2. So nothing really has to happen. Hopefully you started on project 4 already and you're making progress, but you can really take some time to recharge and re-get some energy. Next week, Stephen wanted to remind me of this. Next week, we've got the normal, recorded lecture. Bora did a wonderful job on dependability, parity, ECC, and RAID.
It's already posted. It's
already posted.
Watch it if you like.
Beautiful. Already posted. That's his last lecture. I did my last lecture on cloud computing, which is today's lecture. Then, this is important. We're going to have a wonderful guest from Apple. I don't want to get the name until it actually gets finalized and we're double, triple check that. But we're hoping to have a guest from Apple talk about a GPU and that lecture. And then he's going to be giving another lecture on the 39th live. So we think it's going to be live. So we're going to probably end up using this exact time slot, which is the 4 to 5 time slot for a live lecture on GPU. We're very excited about that. We're going to hopefully announce it formally on Monday. And then please do come live on 12/4. We're going to have the last session live. We're going to, again, cannibalize this webinar to have the last section live. We'll have all the awards for all the prizes. All that's going to be done live. So please do. Next week is recorded lecture Monday, live. We think it's going to be live on Wednesday for GPU. It might be pre-recorded, if so, we'll let you know. And definitely live on Friday, 12/4. So please do come for that. And please note that the Project 4 deadline is 12/2. Don't forget that.
In the last lecture, we're going to have Project 3 prizes. We already have them. Project 4, we have to wait for all. I mean, there are people who have various kinds of extensions.
Yeah, we have at least 6 slip days we have to wait till. So Project 4, we're not going to be able to announce by exactly.
A few extra, probably.
Yeah. Well, and plus, we'll need time. Like once your slip days are done, then we have to run our project competition that's on our side. So we need to be able to make sure that's checking out. Okay.
By the way, if you're missing us, I mean, we are still around.
Yeah. And Bor, do you have any room for undergraduates in your research group? Because I serve the.
We're going to advertise that last week.
Yeah, we'll advertise that.
I've asked my colleagues. We have a ton. I mean,
yeah.
What is about that?
Good job. All right. And I'm hearing that scores are just released, so you guys are all good. I'm so proud of you. I hope that's a great gift for you to have a nice Thanksgiving. We will see you next week on Monday for our live session. Looking forward to that. And don't forget, we think it's going to be Wednesday live session and definitely Friday. So circle that in your calendars. So we'll see you there. All right.
Guys, this is a rare thing. Apple speaker, public.
Yeah, it's going to be
how to design a GPU.
We're excited about it. We're excited about it. Good stuff.
All right. Thank you.
All right. Thank you all. Have a great time. Enjoy time with your families or video or live, and take some rest and come on back, rest and recharged for our final exam. We'll have our final exam details released on Monday, 11:30. Okay.
Thank you.
Take care, folks. Happy Thanksgiving, everybody. Good to see you all. All right. Take care.
All right.
All right.